This one?
What?
All right. Very quickly. Hopefully the first 4 problems were not a big deal, right? So now you can see the notation of these braces. And like somebody pointed out, it's sort of like the limits on an integral in a way, but not really. But sure, what the hell? Tells you what it starts from and goes to. So the first 5, was it 5? 4. Good, even better. So n starts at 1. So it'll be 1, 1/2, 1/3, 1/4. Of course, I got to start here. Just make sure everybody really understands how these are built. Because if you don't understand this, you ain't got a shot at anything else. So, got to start here. But let that be simple. This is just a function that we're plugging values into. Okay, so this is a sequence because it's separated with commas. 2. So the only thing on this one is it starts at 5. So what's the first element?
5, 6, 7, 8.
All right, cool.
9, 10.
Overage here. All right.
No.
Here's one that's a little bit more interesting.
Two.
Good, because at 0, this will be 1. So 1 plus 1 is 2. At 1, 1 minus 1/2,
1/2.
positive 1/2.
3/4.
Yeah, 3.
5/4.
So this is A1, let's say A0. A1. So A2, when n is 2, this is 1 plus 1/4, 5/4. So A3, when n is 3, 1 minus 1/8, 7/8. And then A4. Oh, that's 4 elements in it. That's enough, Jen. That one's interesting because it's always bouncing around 1. But of course, look, this is really simple to see. What's it going to do? Will it converge?
Yes.
Because what happens to this piece? When n gets really big, this piece goes to 0. So it's 1. But because it's alternating, it's negative and then it's positive. It's bouncing around its limit forever. Above the 1, below the 1. Above the 1, below the 1. Did you guys see that?
Yes.
Okay. Oh, and then number 4 was really awesome. But once you see how this works, you'll see how it works. Oh, Yogi Berra showed me. You see how it works. You see how it works. So to get the next element, I need to know the 2 previous elements. So when you first see this, you're like, what the hell's all that shit? I got to tell you what the first 2 things are. Is it 2, right? Yeah. And then you know what A1 and A2 are. You need to figure out what A3 and A4 are. So if I want to know what A3 is, what's N? N must be 3 to get A3, right? And now that I know what the value of N is, that's the variable, I just got to plug 3 in for N. So if you start to do that, I know a lot of you guys were like, didn't trust this. I don't really blame you because you haven't really done this kind of stuff before, but do you see how, this is why they have to tell me 2 values, because A3 is twice A2 minus 3 times A1. And thankfully I know what those values are. This is just like saying f of 1, f of 2, where the function is A, the sequence definition. Everything I just say makes some kind of sense?
Yes.
It really is. It's a function of N. Oh, no, sorry. So A2 is 5, and A1 is
2.
So A3 is
4.
So now I know that A3 is 4. So these are what I know so far. And then how do I get A4? It'll be twice A3 minus 3 times A2. So I get twice 4 minus 3 times 5. Negative 7. Now somebody was asking me, how can you tell if it converges, diverges? Recursive formulas are relatively difficult to answer that question for. So what we do with recursive formulas is we try to write it in this form if we can. So I would write more elements out and see if there's a pattern to them and try to write it like this, because then if I can write it like this, easy. It's easy to figure out what it converges to or diverges. How we know so far? I know, it's just an automatic thing. I can't stop. Alright, so what about the first A? I'm just going to write the thing. We know it's going from 0 to infinity. It's a good question. Somebody asked, would it change the answer if I started at 17 or something instead of starting at 0? So whatever happens in the first, give me a finite number of elements, doesn't matter as far as what it does in the extreme. Does that make sense? When we get to series, it's going to be kind of difficult to kind of keep in mind. The first, 18 billion is still a finite number. Compared to infinity, 18 billion is a speck of a piece of dust on the back of another piece of dust. Right? Which doesn't exist. It's somebody's brain. So this should be easy. You shouldn't have to do a lot of work. I know on this paper I gave you, but remember this little divide by the highest power, that's the reason why the shortcut works. Just use the shortcut. Right? Does everybody know what I mean when I say that? The degree is bigger on the bottom, so this thing is going to go to 0. Or 0, or however you want to say it. Or you can do L'Hopital's if you really feel like it, because it is technically indeterminate.
But isn't it 1? It will be comparative to 1 over n.
Beautiful.
But n is not going fast enough to get to 0, isn't it?
If the denominator...
Compared to 1, n is going really fast, because 1 ain't going nowhere. So, you understand? I mean, 1 over n, as n gets really big, there's no question that's going to 0. Right? And I know this is going slow compared to like 2 to the n. It's going really slow. But you're comparing it to somebody who's not going anywhere. So no matter what that put down there, it's going faster than that guy is. Right? Even the slowest function there is, that still goes to 0. ln is damn slow. And you'll see what I mean here later in this chapter. Slow. Alright.
That's back here, P1 anyway.
Huh? Exactly.
1 over n.
I love it. So you know what I'm talking about. The P thing, when you add an ln, it doesn't do shit. So it's like effectively nothing. I love that idea. So anyway, all right, we'll all get to that point someday. What about part B? This freaks some people out, which is good. I threw out there the idea of squeeze theorem. You guys remember that? If I had this, what is 3 officially? You make this like that so it doesn't look like just, extra n sin.
It's just going to
It's the what? Amplitude.
Yeah.
So I can look at that as the amplitude. Right? Anytime I plug an n in, I get a number here, and that's the amplitude of the sine wave. So some of you guys thought this diverges because sine oscillates, but it continuously oscillates less and less and less. So the really neat thing is if you graph this thing, it ends up looking like, I love this picture. And of course that's going to 0, go to 0, you stupid little thing. All right. So that's the plucked guitar string. Thankfully, this is true, or else every guitar string that was ever plucked will still be oscillating. And we'll all, hey! Sorry. I love that. Damn it, don't do it! Oh shit, there's another one! Pluck! Alright, sorry. So thankfully friction exists. But that's just one possible thing this could be used for to model is a plucked guitar string. But it's the squeeze theorem. This is exactly the squeeze theorem. Right? This is in between negative e to the negative n. I don't know if you guys remember this at all. And positive e to the negative n. These both go to 0, therefore that must go to 0. And that's exactly what we're seeing visually. These both go to 0, which means that must go to 0. Squeeze. Kick ass. Yes, sir.
Do we have to
write that to prove it?
I personally think we're beyond this. I think if you just say to me, that oscillates, sure, but that's going to 0. So 0 times finite is 0. So there's really no need for the squeeze theorem, truly. 0 times a finite number is not indeterminate, it's freaking 0. And poor sine can only go between -1 and 1. So 0 is going to eat that up. Yeah?
So we just wrote that it converges to 0, and then we drew that picture.
Yeah, the picture's awesome, or you can just say something that's going to 0, that's finite. Right? Don't just say equals 0 and give me nothing. Right? But you don't have to do the whole squeeze theorem. Right. The minute I said squeeze theorem, some of you were like, I gotta leave now. But, I mean, it's not really not that. Anyway, all right. What about C? Oh yeah, this is fun. All right, what do I have to use here? Yeah, because it's not a ratio polynomial, so I can't do the shortcut like we did part A. Officially, I have to replace with x's so that I'm allowed to do what I want to do. So the derivative of the top is what?
2x over x squared plus 1.
Beautiful. So the derivative of ln is 1 over the thing, and then the thing gets a turn. The technical term is the thing. Divided by the derivative of the bottom. And the big mistake I see is people always freaking do quotient rule or some shit. I'm not asking you to take the derivative of this whole thing. L'Hopital's is the ratio of the derivatives of the function. So it's not quotient rule or any shit like that.
There's so much easier.
Yeah, of course it is. And of course the minute people learn this, they start doing quotient rule wrong. Well, you just take derivatives. We didn't. Oh. That's what it sounds like to me. All right. What's the derivative of the bottom?
1/3 of
X to the negative 2/3.
Alright, so I can clean this up a little bit, right? So that was application of L'Hopital's. Let's clean this up and see what I really got here. So I can pull 3x to the 2/3 up. Is that cool? So I get 6x to the 2/3 plus 1 over x squared plus 1. Does everybody see how I got from there to there?
Yeah.
So I just did the reciprocal, really, or however you want to think about it. I just multiplied top and bottom by 3x to the 2/3. So it ends up there. Is that indeterminate anymore?
Well, you could use a shortcut.
Yeah, exactly. It's still indeterminate, but it's not polynomials, but all that matters is I can see the degree of each, right? And of course the degree is biggest where?
Denominator.
On the bottom, because this is 5/3, a little less than 6/3, which would be equal. So it's that's a little less than this, which means the whole thing is going to 0. And I understand some of you guys graphed it. You can't prove a damn thing by graphing anything, because I don't care what happens in the first 10 terms. So then you change your window. I don't care what happens with the first 1,000 terms. Then you change your window. I don't care what happens with the first 18 billion terms. It's still not a proof. This is a proof. So be careful by that. Don't just tell me it looks like graphed it and it looks... No. No. Because I will come up with a function that does weird shit outside your window. Okay. That sounded weird. It does weird shit outside your window. What's that sound? Stupid function. Follow me home. Jeez. Alright. What about the second A? I'm trying to make these not too weird yet. They're going to get worse.
N plus 1.
And over n plus
Yeah, this one's not too bad. The tops are all n. The first term is 1, the second term is 2, and the bottoms are all 1 more than that. So yeah, an will be n, 1, 2, 3, over n plus 1, which is actually what I gave you earlier. All right? Started at 5 up there.
Do you have to write what n starts at?
Yeah, so on this one, well, this is like this, and then I could write it like this if I wanted to. So if I write it like this, I'm pretty much assuming it starts at 1. If it doesn't start at 1, I have to write it in this form so I can be more explicit about what it starts at. Does that kind of make sense? So if you ever see something written like this, they either have better said something earlier about it starting somewhere, or it's got to start at 1. That's what this assumes. So yeah, you can write it like this if you want to. N equals 1 to infinity. You ask. Part B, it's only one little step off from part A.
1 over n.
Yeah, because the top now in part B is always 1. And the bottom is n. So again, we can do this if we want to.
Do the first divergence or converges? Is that pretty nice?
Oh yeah, does this, no, yeah, I mean, what does this converge to even? Be even more specific. Yeah, the limit as n goes to infinity of an is 1. So it converges, and it converges to 1.
Oh.
What about part B? Of course, this converges to
0.
0. And to be, now this is where, this is all nice. And it's not difficult. The work we have to do in section 11.1 and the work we have to do in section 11.2, separately, they're not difficult. It's when you mix them up that you get in trouble, and that gets frustrating and turns people off very quickly. Right? I'm not saying any of this turned you on in the first place, but I mean, it just really makes you feel like you're never going to get it. All right. Part C, we sort of did. Now, let me show you a little shortcut. I showed one person how to do this a certain way, and you know it's based on 3n, right?
Yep.
So then you say if it was just 3n, it would be 3, 6, 9. So it's not 3n, it's 3n. How do you get to 1? Minus 2.
Or 3n plus 1, n starts at 0.
Beautiful, but I kind of want you to start all these at 1. But if you define your n to start at 0, you're awesome too. Right? Here's a nice thing. If you have to start at 1, this is A1. What would A0 be if it existed?
0.
Negative.
4 minus 3 is 1. 1 minus 3 is negative 2. Or not. So it's 3n minus 2. And if you look back at the one we did earlier, it started at 4. The answer was 3n minus 1, right? And 3n plus 1. Because what would have been the term before this?
1.
1. Yes.
So we can choose whenever if we want to start at 0 or 1.
Yeah, so let me write both answers up here. So if I start at 1, that's what the answer is. If I start at 0, what will the answer be?
3n plus 1.
3n plus 1. Because 3n is 0, and I have to add 1 to get 1.
So you just make sure you have the right notation.
Yeah, if I ask you this question, most of the time I'll be specific. I'll say n starts at 1 or something. But if I'm not, you just have to tell me where you start at.
Right.
Yeah.
So for that problem, if you didn't tell us n started at 1 and we wrote it the other way, that like
This way.
Yeah.
That's bad.
Okay.
Because, this means, as long as you wrote this like this, you're fine, because this kind of
Yeah,
implies that n starts at 1.
Yeah, that's what we can do it.
So if you want it to start somewhere else, you have to write it the way that you're able to tell me where it starts. Okay. All right. And is that one more? So once you see how these alternating sequences work, you kind of get it. It works this way normally. It'll be this way forever. Once you see how it works, you got it. Is my hope. It should be. So for part D, all right. One part of this is easy because it's basically the same thing as part B, right? So I know somehow fundamentally it's going to be 1 over n, but it's got to have the alternating piece to it. So if I think, okay, maybe if I do this, that would be alternating, right? Does it alternate in the right way?
No.
Or in the right pattern? Because if n is 1, and of course this is all assuming n is from 1 to infinity. If n is 1, this would be negative. So then I just adjust this by 1. So you can do plus 1 or minus 1, doesn't really matter. So now if it's this, when n is 1, that's 2. Negative 1 squared is positive a. Now it matches. That's how you can always deal with alternating. Alternating will either be negative 1 to the n piece thrown in. So you don't even care about the positive. You just look at what's there and come up with the term. It's 1 over n, and then you got to figure out, okay, is it negative 1 to the n to alternate, or is it negative 1 to the n plus 1? Or I don't care if you do negative 1 to the n minus 1. Technically, if you do negative 1 to the n plus 1100, who cares? I mean, 1101 actually do better. Otherwise, you're just not going to the ring. I don't know if you guys are with me on that. It's just a question of, do you start positive? That's what these two would start positive. Do you guys see that? These two would start positive. This one would start negative if n is starting at 1. All right, cool.
Yes.
Some of you guys are fading. You're making me tired. Some of you are like, yeah.
So what if we come up with a sequence, an equation for the first 4, but then they don't work for the rest of them?
That's the worst. It's too bad for you. Sorry. That could happen. And man, I've lived that. So, and it's... what it means normally is you're basing it off the wrong base. Like instead of 2 to something, maybe it's 4 to something, and that's why it captured a few right answers but not all of them, or something like that has happened. So normally that means you're really damn close, and you're not like hopeless. You almost have it, you just did something like that. It's not easy for that to happen, but it can happen. And the worst case would be if it was a typo, and that would be frustrating as hell. So I always triple check my quizzes and tests, because that would be somebody come up and say, I've been working on this for half an hour. I'm like, oh shit, that was my bad. Then you can slap me. All right. So any questions on that stuff?
So that's a promise, right?
Yeah.
Okay.
See, now I'm going to like quadruple check it, just so I don't have a line of people. My third. I have no idea what you're talking like that. So any questions on that first side?
We haven't talked about series at all yet?
Nope. Not a damn word. So real quick, just since you said that, and just because I keep saying, and one reason I didn't want to talk too much about series is just so you do 11-1 homework, just thinking about sequences. But all a series does,
There's a little Greek letter in there.
so 1 over n, this is a sequence, right? It looks like 1 half, 1/3. This is a sequence. A series would actually start with the same little definition in the inside. But what it does is it takes those elements and it adds them up. So you're going to have these summation symbols. And those, of course, have a natural place for the 1 and infinity, for the limits, and that's, of course, what led to integrals way back in time. It's not integration, this is strictly finite sequence of terms, not finite, but a discrete sequence, not continuous. So where people get confused is this sequence, does it converge or diverge? It converges to what? There's no question about that, right? Sequences are always easy to tell, because either you just do what we just did, which is it's basically polynomial ratios, or you use L'Hopital's, whatever. That's relatively easy stuff. You should agree with me, because it's true. Series are insane a little bit, and thankfully we have a lot of ways to kind of check them out, but the reason they're more difficult to get, and I talked about this before, the first thing, when I first told you what would happen if I add up an infinite number of numbers, everybody thought it would go to infinity, and then I quickly proved you wrong. If I add up 0.1 plus 0.01 plus 0.001, that goes to 0.1111, which is 1/9, which is a little far away from infinity, right? But showing that a series converges will be much harder than showing that a sequence converges. Because this, if I add those elements up, it actually is divergent. It goes to infinity. And probably the quickest way to tell that is to actually look at the associated 1 over x. You guys kind of with me?
Yeah.
If you integrate, now go. Summing this is like integrating this. Let me let that sink in. And the reason, and some of you guys might be like, well, that's not fair because there's like more stuff here. If I took little rectangles of width 1, then aren't these areas going to be equal to these? I really want you to understand. It would be the width times the height. And isn't the height the function values? So integrating this is actually exactly, it's not going to give you what it would converge to, but it gives you an idea if it converges or diverges. Let me just let that sink in for a second. Okay. What do you get when you integrate 1 over x from 1 to infinity? ln x from 1 to infinity. Or of course, all right, Jeff, be all technical here. You guys, an improper integral. So what happens? Natural log of t, limit, t goes to infinity. What happens to natural log of t? Goes to infinity. So it doesn't matter if this guy goes to 0, but this goes to infinity. Shit diverges. Therefore, the series would diverge. So that, once you accept that I can add an infinite number of numbers together, and they could be a finite result, like 1/9, 0.11111, then you sort of swing too far the other way. You think, well, these go to 0, so if I add them up, it should converge. No, they don't go to 0 fast enough. They don't get out of their own way. So why is this series so nice? Does this make sense when I say this? It gets out of its own way. The next element is in the next decimal place. It's getting out of its own way. It's not overlapping with itself too much. You could overlap a little bit, but you still got to get out of your way quickly enough. Does that kind of make sense? It's nowhere near technical enough to prove shit, but that's the idea behind what we're doing in Chapter 11 with series. Does it get out of its own way? So some of the proofs of series converging and diverging actually uses that idea. So we'll get there eventually. So this one just didn't do like that one did. It overlaps too much. It actually ends up going to infinity. And what you could do is you can start looking at some partial sums, like S1 would be 1, S2 would be the sum of the first 2 things, so 3 halves. S3 would be the sum of the first 3 things. And you can make a little sequence out of that. But that's, I'm getting a little too far ahead. So can you start to see, if you confuse whether it's a sequence you're looking at or a series you're looking at, when I ask you does it converge or diverge, if you're looking at it the wrong way, you're screwed. Because if you look at this and say it converges because the limit is 0. No, too bad for you. Now, let me see. I'm trying to figure out what I want to focus on for the rest of the day here. I might just want to keep going with this. You guys are like, it's all right with me. I never want to do math induction, but we're going to do that today or next time. Forgot what I was going to say now. Shit. Well, maybe we'll do math induction. I forgot what I was going to say. So let's stick with the original idea. So this is at least getting you started with the idea of what a sequence is versus a series. So you have to be careful between those two for the rest of the chapter. So on the other side of this is some beautiful weirdness called math induction, which sounds painful. Math induction sounds like a dentistry thing or something. Induct your math. But here's the basic idea. This is the idea. I think is too simple, and people don't trust it. They're like, that can't be all there is to it. So someday I'll actually bring dominoes, not pizza, but dominoes, no domino, because the whole idea of math induction is exactly related to dominoes. So if I could prove, if I knew that knocking over some dominoes, so just imagine I have a whole bunch of dominoes on the table. So if I knock down a domino anywhere in there, all the other ones are going to get knocked over. You got it with me? If I set them up correctly, right? So I have a professional domino person, and they exist, right? And they come in here, and they set it up. So I know that if I knock any of them over, if I knock the kth one over, the rest of them will get knocked over. Kind of with me? And then I can prove that I'm able to knock the first one over, then that proves that they all can be knocked over. Now that's not anything amazing. You're all like, oh, is that all it is? I just get to play with dominoes? But here's what it really, really is. Just keep in mind the domino thing. That's what got me through this when I first learned this. Of course, I loved this in the beginning. So I want Sn to be some statement about n. So you got 4 statements about n on that piece of paper, and one of them I've kind of worked out. So if you're able to, well, first thing is suppose that Sk is true. So that's related to me saying, okay, you got this long thing of dominoes. If I pick one in the middle, the kth one, whatever one I pick, and knock it over, they'll all get knocked over. So the kth thing is true. If I can show, if I assume that this is true, and that's where students start to turn off a little bit like, you're assuming the thing is true? Well, shit. But if I assume the kth thing is true and show that that means the k plus 1th thing is true. So if I say it's true here, which implies it's true here, then if it's true here, that implies that it's true here, right? If I couple that with, in fact, I went out of order. Oh, Jeff. So if Sk is true, then Sk plus 1 is true. And I couple that with, this is out of order from the paper, what's called the base case. S1 is true. So the first dude is true. And I prove that if one of them is true, it means the next one is true. Then the statement has to be true for everything, because then the dominoes all fall over. So normally what I do is I show this is true, I assume this is true, and I show that that assumption leads to this being true. Then the whole dominoes fall over, I'm golden. Now that's nice to say, but right now you're all like, I have no idea how the hell to do any of that shit. Right, so let me do the example I worked out here so we can talk about each step. By the way, in the book, this is actually discussed like back on page 76 or something crazy. It's on page 699, they reference it, I think. Yeah, they reference math induction on page 699. It's discussed back on page 76, believe it or not, very quickly, and they have a really bad example in there for you to look at if you want to. Right. The classic math induction looks like series kind of stuff. So that's why this is a good place to talk about. Classic math induction. And these are kind of cool. That did sound really dorky. These are really, kind of cool. Because you get these really nifty, if I add up all the odd numbers up to a certain thing, it's equal to the square of n. So if I add up, let's do the base case, and actually let's do a few more than the base case. I only have to do one. I only have to do the first one. But we'll do a few more just to see if it kind of, just to really enforce that it looks like it's true. So the base case, S1 would mean n is 1. So what do I have to show then? And what does this mean? If n is 1, how far do I go? 2 times 1 minus 1 is 1. So I only go up to 1. N would have to be 2 to go 1 plus 3. Do you guys see how this kind of works? So this doesn't mean that 1, 3, 5, and 7 are always there. It just means start at 1 and go up to this. Well, if n is 1, this is 1. So is 1 equal to 1 squared? Yes, cool. Let's do S2. Well, with S2, I have to start at 1 and I go up how far?
To the second term.
Good. 2 times 2 is 4, minus 1 is 3. I go up to 3. Stop there. You guys semi with me here. You always start at 1. If I'm looking at S1, this is Sn. This is Sn. Let me stop there for a second. What does that stand for? Statement. Or you can think of it as sum if you want to, but it's not always a sum, so no, don't do that. So it's the statement of involving n. So the specific one involving 1, I go 1 plus 3, all the way up to this. Well, this, for n equal 1, is 1. So I start at 1, and how far do I go? 1. So it's 1. Equals, n is 1, 1 squared. For S2, I start at 1 and I go up to
2.
2 times 2 minus 1? 3. So 1 plus 3. And is that equal to 2 squared? Because n was 2, remember? So here, what's S3 going to look like?
1 plus 3 plus 5.
1 plus 3 plus 5. Is that equal to 3 squared? Yes. Holy shit. So these are extra. You don't have to do any more than the base case. Not the basket case. The base case. But these are just extra for right now, just to really, really see what the hell this thing is and how does it work. Okay, yes sir.
So you only have to work on S1, and you're going to worry about the rest?
You only have to show that S1 is
Yeah,
true.
that's fine.
So if I can show that the first domino will fall over, and then I can show that if the kth one falls over, that means the k plus 1th one falls over. Together, that means they all fall over. They all would fall over forever. Right?
So these statements at the beginning would be...
This is showing that the first domino would fall.
No, I mean...
And this is the given thing to work with.
Okay.
Cool. So they got to give me
I
that.
can prove that.
Yes.
Okay.
So I don't know if you guys remember, there was that Riemann sum. Remember sum of I and sum of I squared, and you had, so that's actually number 3 is one of those. So we're going to prove that in a minute. So if you ever felt bad that you could not prove it, now you can. If you never felt bad, then
I don't
you
even
should
know
have.
that.
Oh man, that sucks. So I don't know, Riemann sums, and you had to do the summation symbols before you learned integration. So you had to figure out what delta x was in terms of... Yeah, so it was all indeterminate, and you boiled it down to sum of I squared, with all these weird constants running around. I don't know if you guys remember doing that or not.
It's like
Even if you don't, it doesn't matter. We're just going to prove that statement here in a minute.
It's like before you learned intervals, right?
Exactly, right before you learn integrals. Because the next step is to take the limit of the sum and say that's the integration symbol. All right. So we showed that S1 is true. So now we're going to assume SK is true. And this is where, and understandably, this is where students balk. Because they're like, how can you just assume it's true? I know S1 is true. So if you want to feel better about it, say that this is S1. But I want to show, what I'm trying to prove here is, if this is true, then the next one must be true. And since this is true, then this is true for everything. Then this is like an identity. This is something I'm going to use everywhere. It's really kind of cool. The sum of the first so many odd numbers is equal to the square of the end. It's silly. It's like, whoa, shit. Okay. This is step 1. This was step 1. Here's step 2. So what does SK look like? And this is nothing major. If this is Sn, SK is just 1 plus 3 plus 5 plus 2k minus 1 equals k squared. You with me? As a student, and I still sort of don't, I'm like, why do we have to bring k's into this shit? Let's just use n. But you have to, k is kind of like not n, it's more specific. N is everything. K is you're picking a specific one, but you haven't told anybody which one it is yet. You guys see the difference there? That's actually mathematically important, that difference. So I'm all about it now. I'm cool with it. But I used to never do this, and I drove my teacher crazy. It's not an invite for you to do the same.
Okay.
What would SK plus 1? So we're going to assume, we're assuming this is true. This is just for us, this is damn true. Assuming this is true. Now, do you see on the paper I've got this. Anybody know what this might stand for? What would Teddy show? I don't know. This is we want to show. So I'm going to use that every now and again. It proves this is awesome. We want to show. We want to show SK plus 1 is true. So our goal is to start here. Why do I know I can start here? Because it's freaking true. How do you know it's true? Because I assumed it was. Deal with it. I want to show that if I assume this is true, it leads to this being true. And what does SK plus 1 look like?
1 plus 3 plus 5 plus 2k minus 1 plus SK plus 1.
What do I replace k with? So I get twice k plus 1 is 2k plus 2 minus 1 is 2k plus 1, right? I just put a k plus 1 wherever I see a k. I let that sink in a little bit. Yes, ma'am?
Why is it written differently?
I don't know. Did I put n's? No.
No, it's 2k minus 1.
Yeah, so I was trying to show you, this is where I want you to understand, when S1, how many terms did it have?
1.
1. S2, how many terms did it have? 2. So SK should have k terms. SK plus 1 should have one more term. So I still have all this shit in SK plus 1. I still got up to 2k minus 1. But then it goes the next term, which is 2k plus 1. Just like it went from 1, and then the S2 added, it has 1 in it, but it also has 3. S3 has 1 and 3, but it also has 5. So if SK goes up to here, SK plus 1 has all this in it, plus the next one. So I really wanted that to be clear. Yes?
Why isn't there just a K in between that?
Like a 2k.
Oh, again, I'm working with this form. So if I put a k in, I'll get 2k minus 1. If I put a k plus 1 in, what do I get?
2k plus 2 minus 1.
I see.
And even more fundamentally, all these have to be what kind of numbers? Odd. And 2k would be shit. Does that make sense, Bison? These are all separated by 2. So what's 2 more than this? That. So that's the next one up, right? And you're all like, ooh, this is awesome. I'm so happy we get to do this by ourselves. And this will be on a test. This is awesome. Not much is awesome. All right. That's the new theme. All right. I love this shit. I want you to understand it. And of course you're like, of course you do, Jeff. This is weird shit. So here's what I know this is true. How do I make this side look like this side? What's the only difference from here to there? The 2k plus 1, right? I know this equation is true because I assumed it was. So if I want to add 2k plus 1 to this side to make it look like this, what do I have to do to this side? Same thing. So I'll have 1 plus 3 plus blah, 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 2k minus 1, and then I'm going to add 2k plus 1. I'm going to add 2k plus 1 here. Why would I do that shit? Because I'm trying to prove this statement is true, so I'm going to do what I need to do to make it start looking like this statement, right? Where am I at? K squared plus 2k plus 1. Now that I know I can, it's totally legal what I just did, because I just started with what I know is true, and I added this term in. I can do that all day long. The additive property of equality. Ooh, right? I can add the same thing to both sides of an equation. Yay, us. So I got this side looking the way it's supposed to. Now, the awesome thing, I really desperately want you to understand. Most math induction is all, this is the heart of it, all about what do I have to do to this side, do it to both, and then make this look like this. And if I can do that, I'm done. I've just shown that this does lead to this. If this is true, this would be true. And of course, how do you factor this? Yes. So that means that, and what is the statement? It's a weird question to ask, but what is that statement? That is SK plus 1. So if I assume SK is true, which I know you understand you have a problem with that, I'm not really saying it's true. I'm saying if it was true. If SK was true. We just showed that it leads to SK plus 1 being true. Because I added the same thing to both sides, so of course it's still true. So the first thing is true. No question, right? And even more that's true. But the first thing is true. And also, if one thing is true, the next thing is true. I just proved both of those separately here, right? First thing is true. And then I proved that if something is true, the next thing must be true. Combine those. So if the first one's true, the second one must be true. Well, the second one must be true. Third one's freaking true. Dominoes. All done. Now we all want pizza. Not Domino's, funnily enough. We just like the idea of pizza. Oh. So do me this favor, in the tiny bit of time we have left, number 2 is almost exactly like number 1. Try number 2 out, and then we'll head out.
So I don't like it.
What's that? I won't take it personal if you don't like it. I didn't invent it. I just enjoy it.
Enjoy it too much.
I've been told. Oh, you're cool with this here, right?
Yeah.
And you're cool with I add to this side, I add 2k plus 1. So what do I add to this side? The same thing. Or else it wouldn't be true anymore.
Oh, the K squared changes that.
Yeah, I'm starting here. I do something to this to make it look like this. And then I have to do the same thing to maintain the truth. So this is true. Means this is true because I just added the same thing to both sides. And of course that is sk plus 1. So sk being true means sk plus 1 is true. Golden. Yeah. Golden and weird. I understand. Why I love it. What was that? No, you're not. Don't hurt yourself.